Something like that.
Sorry, what does the 2 times 4 mean in that?
The voltage. 2 times 4 is 8.
Okay.
Oh, I mean, since I have it over here, it's 8 volts, right? But if you want to justify that, well, where did you get the 8? 2 times 4 is 8. Now, let me erase this circuit and draw it again. Because I wrote a lot over here. Let me just, I don't need this anymore. Let me address some issues. Okay. So we have that was what, 12 volts? If I put the units, then it's understood that it is a resistor, right? This one was this a 2 ohm or the 4 ohm? All right. At some point, when I got to the resistor that's equivalent to the other resistors, right? I figured out that the current through that equivalent resistor was 6 amps. And that was a circuit with 1 resistor and 1 battery. So I then realized that the current through the battery was 6 amps. So that means that, you must have had 6 amps over here. And you must have had 6 amps over here. Now, this is called a junction. And so is this. So a junction is where 3 or more wires connect, because then the current can split. This is not a junction. If you have 6 amps arriving over there, you gotta have 6 amps, leaving over there. Right? Charges flow, and so, if you have 6 coulombs flowing in every second, you gotta have 6 coulombs flowing in every second that way. So this is not a junction, not a junction. This is a junction because there the charges can split. Now, if you look at this circuit over here, we can actually look at it, given these numbers, and in our heads, calculate what the current has to be through this resistor and what the current has to be through that one. In 1 second, we can figure that out, given these numbers, or maybe 2 seconds. Because, think of it this way. It may be a silly way of thinking about it, but it helps, and I hope it gives you insight. This 6 amps over here, right? That means that, in a cross section of that wire, there are 6 coulombs of charge going through in 1 second. Every second, 6 coulombs of charge, 6 coulombs of charge, right? So let's think of this as, instead of 6 coulombs, let's think of it as 6 people. So yeah, you got 6 people over here going this way, 6 people, they go, when they get over here, they can only turn right, so then they go right, and that's up the circuit, and then you gotta have those 6 people go through the battery, 6 people, when they get over here, 6 people, well, the only choice is to go to the right, so 6 people, 6 people, 6 people, 6 people, 6 people, but then they get to the junction, now they have to split. So how many of the 6 people are gonna go this way, and how many of the other 6 people are gonna go the other way? And it's like they have a conversation as they approach terminal A or point A in the circuit. They say, okay, there are 6 of us, right? We have to split. Some of us are going to go this way and the rest are going to go along the other path. Now, which of these 2 paths poses more resistance? The 4 ohm. So less of them are going to go that way. And which path poses less resistance? So more of the 6 people are gonna go along the path of less resistance. So, but also notice that this resistance is twice as big as this resistance. So you're gonna get twice as many people through this one than through that one. So give me 2 numbers where one number is twice the other, but they have to add up to 6. 4 and 2. So you're gonna have 2 people going this way, and you're gonna have 4 people going this way. And then you'll get the 2 people going through this. And then you're gonna get the 2 people going through this, and then the 4 people will join those, and you'll get the 6 people going that way. So 6, 6, 6, 6, 6, 6, 6 split, 2 and 4, 2 and 4, 2 and 4, 6, 6, 6, 6, 6, 6, 6, 6 split, 2 and 4, 2 and 4, 2 and 4, 6, 6, 6, 6, 6, 6, like that. So by just looking at these 2 resistors, or resistances, right, their values of their resistances, right, and knowing what the current is over here, you get pretty much, oh, this is twice the resistance of this, so it's going to get half as many people as over here. And given these numbers, you know, what 2 numbers add up to 6, and one number is twice the other one, then 4 and 2. It's if you had, like, you know, a current of 1.734 amps, and you know, then you need a calculator to do that, right? But basically, that's what happens. Yes. And resistors connected in parallel have the same voltage across them. So when these people go from here to here, it doesn't matter if they go this way or that way. The potential here and the potential here are not changing depending on which way the current, you know, goes. So the voltage going this way or that way is going to be the same. What was it, 8 volts? So it doesn't matter. If, you know, these people are going to have to drop 8 volts, and these people will have to drop 8 volts. So that makes them in parallel.
Oh, what if you had a resistor on the junction? So like the one resistor was like feeding it both ways, or does it not work like that?
No.
Okay.
I mean, I could do this, right? But then this is in series with this, and this one is in series with that, and I can just combine them like that.
Oh, okay.
Yeah, I can just move it to add it to this one, then be part of this. Actually, depending on the circuit, right? I mean, usually the resistor has a much greater resistance than the wire, so then you ignore the wires. We could also say that this is the total resistance of this path.
That's so kind of like adding them up kind of
Yeah,
before
yeah,
they're
exactly.
split off into the junction.
Or if it's something that has a considerable resistance, you know, 1,000 ohms, 200,000 ohms, then you just forget about the resistance of the wires themselves. It's like it's all in there. So, question, how many different currents are there in this circuit? 3. There's a current over here along this path. There's a current over here, and there's a current over here. So there are 3 currents. Now, this circuit is simple enough, and that's why I like to discuss this one, because it's the simplest one, and then you get to focus more on the physics. You know, what does power mean? What does energy mean? What do you mean the energy supplied by the battery, or the power supplied by the battery, the power dissipated by the resistors? You know, what do you mean? You know, how do you figure it out? So it's a simple circuit, right? But you can have more complicated circuits. And this problem could also be done in another way, using another approach. Okay? So I like to discuss that other approach, which is useful. Well, it's useful. You know, it applies. It always applies. It's just that in some cases, like for this particular circuit, it's just easier to just think of the resistors as connected in series or in parallel. But there are circuits that can be more complicated, and you can have resistors that are neither in series or in parallel. So what do? So there's a more general approach, technique. for solving those circuits, and those are called Kirchhoffs laws. So let me address Kirchhoffs laws, and there are two of them. I don't really remember how to spell these guys' names, but I think it's like that. I think, or maybe there are two H's in there. I don't remember. Let me look it up. Oh yeah, there are two H's and two F's. So, someone's laws, okay? So, let me talk about each one. There are two. Let me talk about them separately. And then let's put them together to solve the same problem that we just solved. You know, the 2/3 ohm resistor, the 2 ohm and the 4 ohm resistor, and the 12 volt battery. So I want to solve the problem again using this guy's laws. All right? So the first one is the junction rule. So first of all, what is a junction? It's where 3 or more wires connect. In other words, current can split. So, how about I ask you this question first. What if there's a street, another street, another street, and another street, and there are 5 cars coming in? 2 cars go this way. How about 8 cars come in? And I impose the condition that there's nobody parks in the junction. How many cars are here and which way are they traveling? Can you do that in your head? What's that? 11 going outwards, right? Right? Because going in, you have 5 and 8, that's 13. And you got 2 leaving, you gotta have 11 leaving also. No? No? No cars stopped and stayed at the junction. So if you have 13 coming in, you're gonna have 13 leaving. Conservation of cars. Kind of. Okay? How about another one? You know, in case this was confusing. So let's make this one 3 that way. How about I make this one 2? And then I have this one 6. So what must I have over here? They don't even have to be cars. They could be charges. They could be electrons. They could be people. They could be, you know, but no one can stay at the junction. This is the junction, right? You got 1, 2, 3, 4 wires connecting, so currents can split. So what should we have? 7 what?
7 driving in.
Okay. Yes. So how can we write this mathematically? We can say the sum of the cars going in must equal the sum of the cars leaving the junction, right? So, actually we're not considering cars, we're considering charges, right? So, we say the sum of the currents going into the junction must be the sum of the currents going out of the junction. It's a conservation of charge, right? Whatever comes in goes out. No charge accumulation at the junction. In fact, in the circuit that we had, what did we have? We had, at point A, we had 6 amps coming in, right? Well, if this is 4 amps, that must be how over here.
2 amps.
Gotta have 2 amps going away, right? And what happens when you consider the other junction down here? We had the 4 amps coming in from above, and the 2 amps coming in over here. Well, there's no accumulation of charge anywhere. You're gonna have 6 amps going this way. Whatever goes in goes out. Yes? So that's the junction rule, right? The junction rule, just think of it as whatever goes in goes out. It's a conservation of charge statement, right? So it's really conservation of charge in, in circuits, right? So the sum of the currents that enter the junction must equal the sum of the currents that leave the junction. So if you have I1 going in and I2 coming in, you're gonna have I1 plus I2 going out. So, suppose you have this. Suppose this is I1 going in, I2 going out, I3 going out, and I4 coming in. What is the relationship between all of these currents? If you consider the junction, right? So, the sum of the currents going in, which are those currents going into that junction? I1 and I? And what are the currents leaving the junction? I2 and I3. That's the relationship between them. Yes? If we don't know the numbers, but we know their names, the letters, then we can write something like this. So the junction rule is a statement of conservation of charge in the circuits, right? The charges get moving, right? They don't get accumulated. Now, for a junction, right? They could accumulate in the conducting plates of a capacitor, but not in the junctions. Okay? Are we good with the junction rule? Feel happy?